So we now come to the last talk of this session, and this talk will be given by Professor Sudeshna Sinha, who many of us here know her very well because she was a colleague here for several years. Currently, she's the Deputy Director at ISER Mohali, and some of you may recall that just last month also she was here and gave a very nice public talk, which we heard. Today she's going to tell us something more about complex systems.
Well, first off, thank you for inviting me to the party. I'm absolutely delighted to be here. And though Kapil and I are, have been very nomadic over the years, math science still is the place where we have had our longest stretch. So it holds a very special place for us. On a personal note, I think I should also just say that it gave me the space and the openness to do whatever research I felt like doing, the support to do whatever research I felt like doing, and so I'm truly grateful. Okay, so as Meena just said, I was here a month ago, and I had to sort of scramble around trying to find out non-overlapping science to talk about today, and I thought I'll pick up this thread on complex systems because I know there's a lot of expertise in the audience from math science on the subject. So one of the things about complex systems is that the good news for us is that the Nobel Prize of a couple of years ago legitimized this word. It's no longer one of those, slightly shady words where, which you use to push things under the carpet, like a cover-up of stuff which you inadequately understand or, you don't have technical words for. Somehow it was very nice for us to see the word complex systems right there in a citation for a Nobel Prize. It gave us some legitimacy. And the other thing which I found very interesting about the Nobel Prize, because a lot of physicists were a little upset that they did not recognize the names of 2 of the 3 people who got it that year. And that was interesting because it actually tells you how truly interdisciplinary this part of physics is. That 2 of the people who, engaged in complex systems research were actually climate scientists. So, we would like to take this broad picture to, give us a sense of where the field is headed. I'll attempt a very, actually, I should have not written precise, I should have probably written imprecise description of complex systems. No precise definition, I believe, exists, so I'm safe there. Let me just put 3 things which I think should be in a complex systems research agenda. One is it should have involved a large number of interactive components. Obviously, if the components did not interact, they would just be, essentially reduced to single components and no fun in that. And if, of course, even when you put them together, it is just a sum of parts, then it does not qualify to be complex, okay? That also doesn't cut it. So somehow it must do something, and we use the word emergent behavior, maybe use or abuse it occasionally, to say that it shows some new behavior that is somehow more than the sum of parts, and that we are happy to call complex. And in some sense, I should also basically, alert people that at some reductionist sort of picture, you might think that everything that's happening at some level is determined by the physics which operates beneath it. So you have some foundational physics which everyone likes to do, and then stuff builds up sort of automatically on top. But the thing is that the hierarchy is actually very, very complicated. So science at X is not just applied science Y. That is not how it works. And once we recognize that, it also legitimizes the more complex science which follows it. So each stage actually requires new laws. So when I say laws, probably I should have put it in quotes, but at least new concepts to make sense of it. So I had this thing which I stole off the internet, let me be honest out there, but I really like this little cartoon of what mathematical modeling is all about. Now the thing is, a lot of us in complex systems research do what is called mathematical modeling. It's one of those key things which helps us make some sense of phenomena which qualifies as complex. So what do? So we are trying to make a simplified mathematical representation, and the thing which we need to put in there is the key feature. What we think is the key feature is where your imagination comes in. But the key features which play the essential role in interpreting the observed phenomena. So that's what you want to do. So the best models should be able to do it, just like Picasso has got the essence of that, very specific looking, somewhat nasty looking bull with a stylized set of lines. And so there's of course a whole zoo of models. I mean, people do what they feel like doing, as I said in the beginning. So you could have these very simple cartoon-like, what we even actually call toy models. And of course, people go to the other extent of having very complicated and detailed things. And obviously, there is space for both. Both are useful. Researchers do both things. But there is a trade-off. So the trade-off is that, in one end, you will get some broad understanding, So if you make a toy model, it would sort of indicate broadly how things work. And on the other hand, if you wanted quantitative predictions, you would like to make your models which are closer or at least analogous to the real thing. So more like a copy of the real thing. Okay, so it's this end versus that end. And so what I thought I'd do here is that I'd maybe indicate a couple of specific results, which I got actually sitting right here in math science. So I thought, it's a good place to share it with you all. But before I do that, I wanted to give you a small, quick recipe. It's one of those, very, very basic ingredients of complex system models. So the two ingredients that you really must have is a local component. So there's local dynamics. So people like us who do dynamical systems are in business because we know very, very nice, interesting, complicated, chaotic, low-dimensional things, and we can just stick them there. And the other thing, which came more maybe from the statistical mechanics side, was the importance of connections. So you have the local component and you have the connections. You put them together every which way you want, and you study them and, and see what you get out of it. So the second one deals with links, you can think of it as a graph of the underlying connections and the coupling forms. And here is a little table of what I call a hierarchy of models. And the way I have put it is to say which class of models considers various important things, that is space, time, and the state variables, either as continuous, that is represented by a real number, or discrete, as represented by integers. So class of models, for instance, at the apex in some sense would be a PDE, a partial differential equation. Space is continuous, time is continuous, state variables. Do note that the state variables would be the closest to experimentally observed quantity, like maybe temperature, pressure, velocity, chemical concentration, population density, as a lot of people do here, charge density, etc., etc. So PDEs are there. Then a lot of people do what are called oscillator chains, where space is discrete, that is to say each oscillator is an entity, so it has a number, integer associated with it. But time is continuous, state variable is continuous, so you can write an ordinary differential equation for it, but distributed in space. The other thing which I love doing is called a coupled map lattice. So there is, space is discrete, as in there are entities on sitting, say, you can think of it on the nodes of a graph or on vertices, and state variable is continuous, but time is discrete. So it's a map. So it is stroboscopic evolution of the state of the system in time. And cellular automatas, I would put a thing where everything is discrete, which of course computer science loves. And I will probably also indicate one or two results which use that class of models. But do remember, each class brings with it its own counterintuitive flavor. For instance, very simply, if you had a non-invertible, non-linear map like a logistic map, it's capable of showing chaos. You take a one-dimensional map with the same nonlinearity, it can only give a fixed point or can run off to infinity. So, you can see how just discretizing it, so it is not just discretizing, okay? So you must remember each class of models brings with it its own validity, sometimes even being a more natural framework to understand something. So they are not just poor man's PDEs, is all I'm saying for the PDE people in the audience. Okay, so now a few specific things, and I'll finish whenever my time is up. So consider specifically a one-dimensional ring of coupled nonlinear maps. So when I say sites, you might think nodes, you might think vertices, if you think graph-like. So there are these integers, 1 to n. N is the size of your network, lattice, what have you. And each one of them has this real number, the state variable associated with it. That's your physical variable of interest. Now consider a very simple map, which is coupled to nearest neighbor. So it just talks, so I is a site talks to I plus 1 and I minus 1 with some strength of coupling, epsilon. And let us take the local map to be fully chaotic, okay, as complicated as it gets. So you string them together, and no surprises, you get, this is what we call a bifurcation diagram. So running along on the x-axis is the coupling strength. And as you vary coupling, nothing, stuff happens, but it's all still a mess. And nobody is surprised. You had a fully chaotic map, you put them together, you got more of the same. Now, you consider the same system by taking the coupling connections and rewiring them randomly. So this was on a ring, okay? And now you take them and you just cut the links and paste them to non-local positions. So connect a fraction p of randomly chosen sites to two other neighbors. So p equal to 0 is your nearest neighbor interaction, the ring, and p equal to 1 is a completely random graph. So here is a graphic. So this is from Watson-Strogatz. In some sense an obvious result, but made a citation classic partly because they had this parameter which modelers like. There's one parameter which you can sweep going from regular through the what is called the small world limit, where dilute number of random links are there, to the fully random case. So now we do this. Let me do the first one. I take that same old bunch of fully chaotic maps in a network where, of course, the network also changes, but at every point of time, it is random. So it picks up random neighbors as it goes along. And even if you forget everything else that I've said or feel too spaced out to concentrate, I just want you to maybe take this one back with you. So here is the same bifurcation diagram. This is the coupling strength. But now look what happened. So these are still individually, intrinsically, strongly chaotic logistic maps at this parameter r equal to 4. So it's absolutely chaotic, no doubt about it. But when you put them together, now not in a regular network, but in a random network, this randomness of the connections and the chaos of the local thing have somehow given you something which you wouldn't have guessed. So this is one of the things which we expect in a complex system, that you get a surprise which you would not have guessed because it's so counterintuitive. So you have made things more random, and what you get is the stabilization of the fixed point. So this thing here just says that all the way from around 0.6 or so to 1, it's a large range of coupling. Every single map, so this I think had 500 logistic maps, all of them sit happily, stably at the fixed point, which is actually a strongly unstable fixed point for the individual map, okay? So basically the dynamic random links has created this window of coupling parameter space where, put it a little more technically, the spatiotemporal fixed point has gained stability, okay? And there is a certain bifurcation parameter, which of course we in the business like to put a number to. And as I said, so all the sites then are stabilized at the strongly unstable point of the local map. This is the takeaway from this bit. Of course, we are in the business of doing theory, so you have to do some stability analysis. As it happened, it's actually a a little bit technically difficult to do, partly because the connection matrix is changing and is random. So, you know, the Jacobian is a little bit of a issue to do exactly. However, you can always turn around something which is a bit of an issue and see what you can make of it. Here, what I thought was that, okay, since the connections are changing, each site is seeing like a blur of its neighbors. So it's like a time averaged mean fieldish thing. And that, of course, simplified things. So sometimes when things are moving too fast, you see, you know, it's like, you know, you actually see something which is a near constant. And if we do that, one can do the analysis quite easily. And the end point is that you get almost no stable range if you have regular connections, whereas for a fully random connection, you get the largest range. So that is where the surprise is. So you throw in randomness in the connections. Of course, locally it was very chaotic anyway, but that connection, the randomness somehow killed the chaos of the local map. And this is a small summary picture of the analytic result, which is the solid line, a little bit of the kind of approximation for small p, and simulations from whole bunch of lattices. So when we get things like this, we are happy because, you know, that solid line is pretty much sticking to simulations. Okay, and this is just to say that, okay, I showed it to you for the logistic map. Anyone, including the referees, will say, but so what if I had tent map, would your answer change? Or if you have a circle map, would your answer change? And well, you don't expect it to change because what really is necessary is the local maps kind of instability parameter. And once that is there and it's equivalent, you actually get absolutely equivalent results. So that sort of is what we you know, say, shows some sort of generality of the broad observation. So this was dynamic rewiring. So I took this map, and at every point I was switching around the connections. So not only was it picking up random neighbors, it was also doing it as it was going in time. Okay. What if we had random connections, but it was static? So, you know, I had a network, random in space, but not in time. So if I took a snapshot, it would look the same, but, you know, the next snapshot changes for dynamic, but not here. So what happens there is that actually what you got for dynamic random connection disappears in the limit of large lattices. So you're back to what you got for essentially regular lattices. And so now you have to make sense of this scenario, that not only is the dynamics on the nodes important, the dynamics of the network is also important. Okay? So that is maybe, this is a kind of halfway or whatever, two-third way summary. So the, two-third, okay. So, you know, I'll just talk very fast and finish everything. So, yeah. So this is kind of, you know, you can take back this maybe, is that the regular lattice gave spatiotemporal chaos, static frozen links gave spatiotemporal chaos, dynamic rewiring, that is switched random links, gave you spatiotemporal fixed point. These are not subtly different things. One is at one end of the spectrum and one is in absolutely the other end of the spectrum. So it is very dramatic, very, very stably different results. So that's the fun part of it. Okay. So of course, static and dynamic gave different stuff. So what do? You employ a whole bunch of students to do this, that, and the other, and, you know, check it out for different scenarios. And I'll just have one picture. Here actually the young person involved was a CMI student doing one of those KVPY things. So that's why I thought I'll put it. Has a little Chennai connection. So on one side is the time period of rewiring is 100 and the other one is 1. So this one is rewiring very fast. The other one is rewiring slowly. So when it's rewiring slowly, it opens up a smaller stable regime. When it rewires fast, it opens up a larger thing. So, of course, we went across the spectrum, looked at different fractions of random links, and different network rewiring frequencies. And this is what, a lot of us in this business call a collapse of data. That is to say, you have to find out on the x-axis the combination of variables such that what you get on the other side collapses to a neat function, which would then indicate that that was the important parameter. So here, P in itself did not give collapse, F in itself did not give collapse, but the product of P and F, everything collapsed, which means that the real thing that was important here was a trade-off between how fast you rewired and how randomly you rewired. So you could actually get the same effect for slow rewiring if you had a lot of spatial randomness, or if you rewired fast, even one or two random links would cut it. Okay, this is in layman's language what this graph means. The next bit are just a set of pictures. Okay, so as I said, I had put a set of models. This one was coupled map lattices. The next two are, this one is going to be what would be called, oscillator chain. Okay, so this is ODEs on a ring and later on a network. Okay, and this particular one was modeling biochemical pathway of a 3-step reaction sequence. And for no reason, I'm just flashing that these were the equations. Okay. Now this is the result. So on one side is P equal to 0 means a regular ring. Time runs up like that, and the rings which are, and the cells, which are 100 of them, 0 to 100, runs along the x-axis. Now when it's a regular ring, there is some sort of, disorder, at least to the eye, and if you, get order parameter, indeed it's there, disordered. Whereas even if we put a dilute amount, if this is P 0.05 disorder, very, very small amount of randomness, it sort of irons out this whole thing, which meant that all the cells essentially come to a synchronized state. So here, randomness aids synchronization. In the first part, randomness aided the fixed point behavior. Here, it is a cycle, but they become synchronized cycles. And indeed, this transition, this is just for the few people who are stat-makey in the audience, that this transition is a P tending to 0 transition. That is to say, with the slightest disorder you throw in there, it very, very quickly goes to synchronization. I thought I'd show one more pretty picture. This was done by a student in ISA, and this was done well before COVID broke, 2013, so that's why I thought I'll show it. It's always nice to see infection spreading before the event. And this I also thought I'll show because it falls in the class of models which is a cellular automata. So these are SIRS dynamics on a network, but SIRS done as a cellular automata. Okay, so this fell in the third class of models. I thought I'll pick up one from each class. So this one was in the third class, cellular automata class. And this is one representative picture among many which he had. So there are these 3 panels. The time period of network rewiring is very fast on top, somewhat medium in the middle, and slow down here. Okay, so the slow down there meant that, so what did the top panel mean? As you see, there seems to be large peaks. So basically your infection spreading has given rise to these sort of, synchronized outbreaks, which is a dreaded word now. It wasn't in 2013. You could happily write a paper without feeling, anxiety. But this showed actually that if you have a random underlying network, you will actually give rise to synchronized outbreaks. Sort of, common sense in some ways too, but nice to see it come out of a model as well. And if you actually rewire very slowly, you have this sort of endemic, small, irregular background, but at least not everything building up periodically together. So here too, to come back to this whole thing of randomness gives rise to regularity theme, randomness gave rise to synchronization. So the central observation was this quasi-fixed low state, kind of like endemic, gave rise to the self-sustained oscillations, which you could think of as periodic outbreak if you switched links more frequently. Okay, so the disease cycles of these individuals on this network got synchronized, and stuff happened. So the last bit is to show one more effect of a random link, and this time it is doing something completely different. So my student, well, the lead of this was Anshul Chaudhary, and so he was a really good student. So when he came and said that his program was blowing up and giving these dreaded NANs, of course, anyone else I would have said go and, fix it and come back next week. But I had to take his thing very seriously. And so indeed what he had was, with a certain coupling scheme, his oscillators were giving unbounded growth under coupling. And this is a bit distressing for anyone who does dynamics. So what I went and told him to do, and he did very, very sincerely and well, was to take those same set of oscillators, which were blowing up, and when they were on a regular ring, I said, okay, now you change around the connections, put it on a random network, and see if the randomness in the connections reigns in your dynamics. And indeed, what happened was that the blow up, which was occurring for the ring, was prevented when you manage to rewire fast enough and randomly enough. Okay, so again, in some sense, the randomness killed the unbounded growth. So the infinities were reined in some sense. And this is the last figure from there. And this was a Fitz-Nagumo model, which is a sort of a model neuron, and he put it in a ring. And with his scheme of coupling, things were blowing up. So this red line here was his regular ring. So, if I let it go, it would hit the ceiling and beyond. So it's already doing, shooting up extremely fast. Whereas these guys here are the ones with rewiring. And this is the phase space plot. It's not showing as dramatically. So this red one comes in and then runs off, to infinity. And the membrane potential just blows up if it's on a ring, but you throw in a few random connections, and there you are managing to rein in everything into a nice bounded part of phase space. Okay, I had 2 more slides. I don't know whether to show it or not. Okay, I'll just show it since I think I have 2 minutes. So I just wanted to say that was random connections. But I had these 2 ingredients, local dynamics and connections. So I showed the part where the local dynamics was fixed and the connections were changing. You could do the same thing by keeping the connections fixed, but seeing how heterogeneity in the nodes affects it. And in more recent things, with more recent students, we sort of found, I've just listed it here, that heterogeneity suppresses chaos. So there again, more disorder, or at least more heterogeneity, more kind of variety in the constituents, did manage to rein in what was more complicated looking phenomena. And this could be asymmetry in the nodes in terms of the nodal dynamics, or it could even be time scales. So same sort of thing, but with ill-matched timescales. And this is actually an experiment which Puneet's group had done on this, and with oscillators. And this flat portion shows how things were, reined in, suppressed when things were heterogeneous, and this off position is when left to its own and just homogeneously doing something. So heterogeneity actually pulled it all back. So basically it's a way of seeing it is that, it has nothing else. There's no other solution which fits everybody except the fixed point. The whole point, of course, is the fixed point stable? That's the story, of course. Okay. And this is my last slide, and I'm done. So I just thought I'll give you a flavor, because a good part of what I said was done, in math science. So it falls on the broad umbrella of complex systems, more specifically linked local chaos maybe, and has some relevance to complex networks. where the basic point is that there is nodal dynamics and there's connectivity and they play off against each other. And in this interplay is the surprise and sometimes counterintuitive things. And the counterintuitive thing which I indicated was that the random links can suppress local chaos and induce global spatiotemporal order. And also I sort of touched upon that these random connections can mitigate catastrophic blow-ups. I'm done. Okay.
Thank you. Thank you very much. On behalf of IMSC, I'd like to present a small memento.